Hello, everyone. We'll do this. I think it will be a nice and sweet talk. We have a few slides that we'll go over to settle the environment and give you some context on what we do and how we do it. And then we will do a live demo using a system that does this linking, this entity extraction and resolution. So I hope you'll enjoy this presentation. Well, first of all, who we are. And I think I'm not going to go through the entire corporate information on LexisNexis. Just for your own knowledge, we are a company that has been in business for 35 years or so, data business. Large data. At some point, the large data that we had became big data. I don't know when that transition happened, but essentially it's more of the same. We just do a lot of data processing. And we've been doing this for the longest time. And we've been, as you can see here, we've been acquired by a company called Reed Elsevier, which is a worldwide publisher, back in 1994. And since then, we continued growing we not only continued growing in our digital assets and our data services, but also we expanded. We started using some of our core technology also in some of the other companies within Reed Elsevier. So even the type of technology and the type of big data processing that we do for our core business in LexisNexis is now being used across Elsevier and Reed. Many of you probably know Elsevier. Elsevier is one of the major worldwide publishers on scientific data and journals and papers. And some of our customers, and this only, as we said this presentation, we were trying to make it more directed towards government use. So these are some of our government customers. We have a large number of vertical markets that we sell data services to, but in general, you have some of those numbers there. Most of our data is US-centric. Although we are expanding internationally, we have some smaller operations in some other countries. And we have a number of vertical markets within the US in the commercial side of things. But we have a significant penetration also within government.
And again, I'm Mary Galvin, and I'm in the LexisNexis Special Services Group. So we're the team in LexisNexis specifically stood up to deal with DoD and intelligence community types of customers. So traditional LexisNexis, Flavio mentioned this, but one of our data sets is U.S. public records. So outside of intelligence, these are just some areas that we work in the federal government. The use case in HHS and tax and revenue is fairly similar, where we help those agencies uncover fraud, so fraud, waste, and abuse types of scenarios. Law enforcement, you can use our public records data set and the underlying core technology to develop comprehensive profiles of suspects. Now, you've got to have permissible use to go ahead and search somebody, but I'm allowed to search myself. So to give you an example of what this system does, I search my name. It pulls up all my past addresses, my relatives, associates. I've got an FAA license from about 10 years ago, so it generates all of that on me in sub-second response time. So again, some very cool things you can do with the public records data set and the key technology that's running behind all of this that we're going to speak to more as well. And then a lot of you probably know how we're used on the legal side of things through case law and that type of thing. But again, legal is another major market for us. Now, transitioning from our online public records data set to something a little bit different, we've got customers with national security mission that they don't necessarily have a need for U.S. public records data, but what they do have a need for is being able to do with their data what we're able to do with our data. So massive ingest, massive profiling, big data. We talk about the 3 Vs. We've got customers that have big data problems. They've got very similar use cases to how we use our data to solve our own problems. So for the national security applicability, they're not necessarily tapping into the public records data set, but they're taking this high-performance computing cluster technology, they're putting it behind their firewall, and they're doing things such as what you see number 2 here, supply chain fraud, visa and passport fraud, and number 3 on this slide, what you see is identity resolution and graph analysis. So being able to develop a comprehensive profile of an individual, kind of like I spoke about in the law enforcement use case, but developing these profiles of individuals on foreign entities and people that are of interest for national security purposes, and then having some sort of graph analysis built on top of that. And then what I just wanted to speak briefly, I kind of glossed over number 1 for national security applicability. But the same technology, we had a success story where we had a client, they needed to prove a concept in about 60 days. And thanks to our technology being on the Amazon Web Services, on the Amazon Cloud, we were able to help them meet their deadline. So again, if you've got a rapid prototyping project, you don't have time to stand up an HPCC cluster, you can go ahead and do it on the Amazon Cloud, assuming that the data is unclassified. And this was all open source data that this one client was using.
So the next couple of slides are going a little bit more specific on what this linking and the analytics type of problem is. We are going to cover in this one presentation particularly what is called entity extraction and resolution. You have a number of data attributes or data elements that are referring to a number of entities, and entities can be defined in any way you want. They don't need to be necessarily people or assets or businesses. They can be topics in a book for what it's meant. The technology is completely agnostic. But essentially, you have a number of observables, which is this data records, data attributes, and a number of entities behind the observables that you're going to try to disambiguate. So there are 2 different problems there, essentially. One of the problems is finding which entities are these observables referring to. And if there are groups of attributes that are referring to those entities, you want to agglutinate, to clusterize those groups of attributes by joining those records. The other type of problem that we will solve in this, and we will see some examples and a live demo on it, is to find relationships across entities. By knowing all these things about the entities, can I say more things about their relationships? Can I find entities that in some way co-occur or are closer in a certain number of dimensions? And we'll see how we apply this to our own data problems, but how this can be applied to a number of other problems. This is a typical segmentation problem, which clustering techniques like this are normally applicable to. You can see that some of the things that you might need to focus on, of course, are around finding those relationships across entities and particularly finding the strengths of these relationships. How close, now let's go back to the people example, which is easier to relate to. If I know that these entities are 2 different persons, and I find out that they are related in some way, how strong and what type of relationship do they have? Are they relatives? Are they associates? Have been they related through 1 or more transactions? How they have been connected in the past? What happened on the time series in connection to that relationship? And you need to be able to use some higher level definitions as you go through this process. Things like, for example, handling properly fuzziness. We all know very well that data tends not to be completely exact. Data has some degree of truthfulness to it, but sometimes it is not as truthful as you expect. There are errors, there are typos, there are missing data attributes, and there are sometimes intentional tweaks on the data that you would want to rule out. Essentially, if someone was trying to change the data so that I can't provide the adequate inference on that data, well, I would like to know as well. So there are a number of things that we can also, and we also take into account, but the interesting thing of this is that we allow the data analyst to express these things in a high-level language, in a high-level programming paradigm. So it is much easier to deal with these details without getting into the underlying architecture of the system or the structure of the data itself. And these are some of the challenges. Many of our customers, either when they deal with their own data, and we will see the technology that we use in a moment in the next slide, and we also have the same type of challenges. Of course, I could come up with a number of rules to do this linking. I could say, well, I know that if two entities have the same, speaking about people, first name and the same last name, and they live in the same address or the same city, they could be referring most likely to the same person. And that might seem to be a sound rule if you are talking about me. If you have a Flavio Villanustre living in Atlanta, and there are two records with the same attributes, there is a very high chance that they are referring to the same one. But what if those records refer to John Smith in Atlanta or New York? The chance that these two records refer to the same entity is a lot lower. So what if we are not talking about people? What if we are talking about entities that are, I don't know, topics in a book or items in a warehouse? Do the same rules apply? What if I'm talking about people information but from using a different language or a different geography where these relationships might be expressed in a different way? So yes, we can come up with rules, but rules normally fall short when you are trying to generalize the problem. And they are also very hard to maintain. If you need to maintain these rules over time and you have hundreds or thousands of different rules to build these links, it becomes quickly an unwieldy problem. And many times it could be much easier if we had complete dictionaries of people. If I could find a book that tells me about everyone, then it might be a lot easier for me to precisely identify these observables in the data. But if I had that book in the first place with all the information, why would I need to even do my data processing? There are no such books. You need to use probabilistic inference to identify these entities from the data itself. And the last one is very important, and there were a few presenters before referring to this problem as well. When you have a very large graph, and when I say very large graph, I say a graph that doesn't fit in memory in a single machine. It doesn't even fit in memory in 100 machines many times. You are talking about billions or trillions of data attributes across billions or trillions of vertices and edges. Partitioning those type of graphs in order to be able to still produce the inference or doing the analytics that you need to do from that graph is extremely tricky. And yes, I know you can partition the graph in some way based on some dimensionality, and then you just swap the dimensions and partition it in a different way and repeat the process over and over until you come up with the results that you're expecting. But this might be really unfeasible. If the size of the graph is large enough and the number of partitions is also large enough, doing this iterative processing on the partitioning and repartitioning of the graph in order to be able to fit it in a large system could be very, very difficult to extend. Now, one step down into the technology that we use. This is what we built. This is a very high-level view of the architecture of the system. But essentially, back, and I alluded to this in the panel yesterday, back 12, 15 years ago, we recognized the limitations of traditional technologies, and we decided to build our own technology to do this large-scale data manipulation. So we built a platform that runs on commodity boxes. Each one of the boxes has its own local storage, local hard drives. This is very cheap, essentially, storage. But it has the platform itself has the ability to manage the data partitioning and abstract this from the problem that the data analyst has at hand, which is analyzing data. It exposes a high-level interface to a data analyst in terms of a very high-level declarative data flow-oriented paradigm. We built our own programming language called ECL. Oh, by the way, all this technology is now open source. We released the entire platform and the ECL language under open licenses 2 years ago. So it's all available. All the source code is C++ for the platform, and of course ECL, which is high level, is all available in GitHub. You can go there, drill through the code, download it, fork it, please, provide contributions. It's all available. It's all free, and you can use it as much as you want. So we built this high-level programming paradigm. Again, this is declarative, and it's familiar to a data analyst. If I have a phone book data set, and I have a customer data set, and I want to join this by first name, last name, I can say, join phone book to customer database. It's just a single instruction in ECL. Now, the fact that the data is partitioned across 100 nodes, and that this join implies doing a lot of low-level operations, perhaps a sort, merge, join underneath, to be able to do this, doesn't matter to me. As a data scientist, I don't care how the system looks like underneath, as long as it can efficiently do what I'm asking it to do. And this is the other thing. ECL, when it gets compiled, ECL is a compiled language. When you submit ECL, ECL gets compiled into low-level C++ and eventually into machine code, and it's deployed on the system and executed in parallel. Many of these problems are embarrassingly parallel, so all the nodes can process their own piece of the data in a semi-standalone fashion. But of course, there are a number of problems that require data exchanges, and the platform handles those. And this same ECL language is used for two different types of clusters or architectures. One is the backend processing. This is Thor. This is more or less equivalent to what you do in a Hadoop world. The difference is that you are not constrained by the map-reduce paradigm. You don't need to be, you are not forced into thinking in terms of mapping data, shuffling data, and reducing data. You can express things in high-level language. And also a data delivery platform. This is a real-time analytics platform called Roxy. The same way, distributed, share-nothing architecture, local storage. Data locality is important in both cases. And they also programmed in ECL. In the case of Roxy, what you build in ECL are these queries, essentially store procedures in a traditional database, and expose those over a front-end web services interface. This is what I was saying before. And this is what is also called, and this has been known for many, many years, as probabilistic record linkage. You use the information in the data itself to identify the entities behind the observables. And you identify the probabilities of observables referring to particular entities based on the specificity of those observables. If I know that a name is extremely uncommon, or perhaps the combination of a name and an address, and I see two records that have the same combination, there is a high chance that those two records are referring to the same person, the same entity behind. Conversely, if a particular value is extremely frequent, having multiple records that refer to those values might not tell me much about the underlying structure of the data. This is a clustering type of processing, essentially unsupervised learning. You can provide some hints to the system, and based on those hints, you can improve the linking. But for the most part, the system extracts this information from the data itself with probabilistic inference. And of course, we use fuzzy matching, edit distance, phonetics, sound XD, metaphone type of stuff. And some of these things might apply or not, depending on which language you are using. If you use soundex, phonetic matching That applies very well in English. It doesn't apply very well in other languages. But you can use some of the other more probability-based metrics to even do linking in any language. This is what I was showing before. If you have a very extremely uncommon name, it might be simple to say that any record that has that name, even if the name is not exactly well typed, even if there are typos, they are all referring to the same entity. Conversely, if you have an extremely common name or set of attributes, saying that those records are part of the same group or are referring to the same entity is a lot less direct. And most likely, you won't be able to say that. And the process is iterative. As the system goes through the data, the entire data set, and compares every record with every other record, and identifies clusters, it will use the information that it extracted by building those clusters to build the next set of clusters and to refine the process over and over. Perhaps those records referring to John Smith were so inspecific that we couldn't pinpoint a single entity. But once we find relationships between that John Smith and this Flavio Villanustre, perhaps the question changes, and I should ask, how many John Smiths does Flavio Villanustre know? And perhaps it's only one. So now you can go back and link those records about John Smith. And of course, we use also a number of more specific dimensions that are processed in a special way, like, for example, time, the time dimension. And in the case of people, well, you are looking for particular attributes, like, for example, the fact that they cohabitated. And again, this depends on specificity. If I cohabitate in a building, in a huge building that has thousands of people in, perhaps that relationship is not that strong. If we cohabitate in a detached single-family home, the probability that we are strongly related is much higher. Now it's almost the rest, all marries. We are going to go through the specific details on the type of linking process, and we'll see a cool demo that I think you'll appreciate.
So Flavio talked about the HPCC. We saw that diagram of Thor and Roxy and the capabilities, and how both of those engines are use the enterprise control language. Now, taking ECL one step further, what we did as a company is we encapsulated all this knowledge that we had around the identity resolution problem and packaged it into what we call the SALT, or Scalable Automated Linking Technology, specification file. So essentially, in 42 lines of SALT, that gets compiled into, you can see the numbers here, about 4,000 lines of ECL, which gets compiled into the C++, and then run on the HPCC system. So the point of this slide is to show that through defining this SALT specification file, you can run a series of data processing steps that, in essence, no time once you define the specification file. So capabilities in SALT, you can do profiling with your data, and you will see all of this in the demonstration, but you can profile your data, parse your data, cleanse your data, standardize your data, and then the idea being, once you've completed these steps here, you can move into the more complex clustering and linking to find those identities and relationships in your data. Now, I'm going to be showing a product that we have called SmartView, which is built on top of SALT, the Scalable Automated Linking Technology, which means it's built on top of the HPCC. Note that with SmartView, basically every layer we add, it makes it easier and easier to use our technology. So even though this number here, the 42, might be a little bit misleading, because even though it's only 42 lines to run these complex data processing algorithms, they're 42 very complex lines that it was very difficult to get our user base to try to learn, basically. So what we did is we created this visual interface on top of SALT, where no lines of code are required. It's purely point and click. And what you can do with this tool, you still have to have an understanding of your data and in the mission that you're trying to solve, but you don't need to use command lines or deal with our own IDE that we have. Again, everything is visual, point and click. And so with that, I'm going to jump to the demo, and I see that I'll just show this really quick because we're at 2:30, and I don't want to cut it into the next presentation. But what you see here, actually, we have something kind of a little bit, not necessarily national security use case, but we took IMDb, the International Movie Data Set, plugged it into here. This is SmartView. This is the application you can get our entity resolution capabilities in. And what you see at the top is SmartView kind of divides the entity resolution process into 6 steps, starting with creating your project and going all the way down. I've already done this with the data, but what you're seeing here is a visualization of my IMDb data. So what I'm trying to find now is how is Meg Ryan related to Robert Downey Jr., and that's building out on the screen. And I'll show one more thing really quick, and I'm also happy to show some demonstrations on the side. But we had identities are the easy use case to kind of relate to, but we also had shipping data. And with the shipping data, what we did is the shipping data had fields like ship name, shipper name, consignee value, so who's receiving the shipping data on the opposite end, contents, and just various levels of dimensions of the fields. So how do you know how to cluster this data or group the data? As Flavio mentioned, if you don't know, this is all unsupervised learning behind the scenes. So the tool went ahead and automatically clustered the data for us to give us a better understanding of what the data was telling us. So what is the shipping data telling us? With SmartView's profiling feature, again, not having to do those 42 crazy complex lines of code, these bars all represent various fields in the shipping data that I mentioned. You can get a quick breakdown of how well the data is populated, but then I could look at my shipper name values and, again, just see my frequent data patterns within that field, frequent values within that field, just to get an idea of what is in this field. Next step in this process is to run specificities on each of your fields. And again, Flavio spoke to this, but the idea being what you're seeing here is, let's take shipper name that has a high specificity of, the average specificity is 9.9. So in essence, shipper name is more unique and there's more variance within that field than ship name, which only has a specificity of 7.35. So when you're comparing record against record, the shipper name should be given more weight in the overall linking process. And I'm 3 minutes over. I could talk about this a lot more, but I really don't. I want to be cognizant of time. So.